This is going to be a tutorial class on the concepts that we have covered in for equations of motions, mostly in Navier Stokes equation. What we have seen in the previous two classes is from the fundamental concepts of derivatives, their different types, the equation of continuity and the equation of motion. We have a comprehensive system right now which could address any of the fluid mechanics problems, at least up to the point of governing equation. The concepts behind choosing the boundary condition will remain unchanged from whatever we have discussed previously. So, just a quick recapitulation of what we have done over here is what you see. This is the equation of motion. When in the equation of motion you add the constant rho and constant mu and equation of continuity, what you get is Navier Stokes equation. So, this is mass per unit volume multiplied by acceleration. So, this becomes force per unit volume. Similarly, del of P is also force due to pressure per unit volume. This is viscous force per unit volume, and rho g is gravitational force, or the body force per unit volume. So, all terms in Navier Stokes equation are nothing but force per unit volume, and a special case would emerge if you assume that it is an inviscid fluid or the viscosity of the fluid is insignificant. So, if the viscosity of the fluid is insignificant, what you get from Navier Stokes equation is something which is known as Euler's equation for inviscid flow of liquid, where this mu term would simply be dropped, and what you get is this Euler's equation where rho times dvdt is equal to the sum of the surface force, mainly pressure, and body force, which is gravity. Now, the expressions for different components, x, y, z components of Navier Stokes equation in Cartesian, cylindrical and spherical component are given in any textbook. You can refer either to Bird, Stewart, Lightfoot, or you can also any or Fox, McDonald. Any of the textbooks will contain the expressions for Navier Stokes equation in different coordinate systems, the x, y, z components in Cartesian, cylindrical as well as spherical component systems. So, what you need to do in that is first see what is the what kind of a geometry you have in hand, then accordingly choose whether it is Cartesian, spherical or a cylindrical geometry has to be chosen. Then find out what is the principal direction of motion. If it is one dimensional flow, let us say flow in the z direction, then you choose the z component of equation of motion and simplify the terms which are not relevant for the in that context. If it is flow in two dimensions, then you have to, let us assume you have to analyze both the x component of equation of motion as well as y component of equation of motion, and then see what kind of simplifications you can suggest in order to make the problem, make the set of equations solvable, hopefully by an analytic method. If not, we have to think of other methods, including numerical techniques, to solve such problems. So, the table for these equations would look something like this. So, this is from Bird, Stewart and Lightfoot, and what you see here are the Cartesian coordinate x, y, z. What is the equation of motion? Cylindrical coordinates r, theta and z. What is the r component of equation of motion, theta component of equation of motion, and z component of equation of motion? And in spherical components, r, theta and phi, the different components of motion in three different directions. So, these are available in any standard textbook. This is from Bird, Stewart and Lightfoot. So, what you need to do is, from these 9 equations, first you have to see which equation is going to be relevant in your case. Is this Cartesian, is this cylindrical or spherical? Let us say for the case of flow through the tube. For flow through the tube that we have analyzed so far, the direction of motion of the fluid was in the z direction. So, first of all, in a tube we must choose the Cartesian coordinate system. Once I choose the Cartesian coordinate system, I will also have to choose what is the principal direction of motion, that is the z component. So, in the table that lists the different components of Navier-Stokes equation, I must choose the z component of the cylindrical version of Navier-Stokes equation, because my principal direction is in the z direction, and then cancel the terms which are not relevant. So, I will in this tutorial part of the course, I will pick 3 problems that we have done in our using our shell momentum balance. One where a fluid flows along an incline, it is a freely falling liquid film, that means there is no imposed pressure gradient in the direction of flow. The flow takes place only because of gravity. In the second problem, the one that we have done is where the flow is taking place in a tube and there is a pressure difference as well as the gravity is acting downwards. And the third problem that we will look at is where we have a tube, the flow is from below, the liquid reaches the top of the tube, spills over and starts flowing along the sides of the tube. So, these 3 problems we have put considerable effort in obtaining the difference equation, and from the difference equation the differential equation. We would see, and I am sure all of you would agree with me towards the end of this class, is that the Navier-Stokes equation, the use of Navier-Stokes equation is the way to go for solving the problems of fluid mechanics, solving the problems of fluid flow, the differential fluid analysis of fluid motion. So, we start with the first case where there was flow along an inclined plane, no pressure gradient, only gravity. So, this was the case which we have drawn. This is the plate and I have a flow of liquid. The dimension, this is x direction, this is z direction, and in the y direction the film is assumed to be, the plate is assumed to be really wide. This is the length and the angle is beta. The thickness of the falling film is equal to delta. So, let us see if we can simultaneously find out which equation that we need to choose from this table. First of all, one must see that I have to choose if this is a Cartesian coordinate, cylindrical or a spherical coordinate. So, obviously, it is going to be a Cartesian coordinate system. So, I am going to restrict myself to B6-1, B6-2 or B6-3. The principal direction is in the z, principal motion is in the z direction. So, I must choose the z component of equation of motion. Okay. So, if I choose the z component of equation of motion, then I am going to write the z component, either the expression that you see here, everything is expressed in terms of velocity, but you can also use the component, the form of the equation where instead of everything in terms of velocity, it is expressed in terms of shear stress. That is the same thing, except mu times del v del Vx del x is simply going to be del square Vx by del x, we can express it in terms of shear stress. So, that is the same thing, this is what I am talking about. In here, the same equation that you see in the next page, where everything is in terms of velocity, here everything is in terms of shear. So, in some cases it would be beneficial to work with the shear stress form. In some cases, it would be more convenient to use with the velocity gradient form. Okay. So, you can choose which one is you are comfortable with, but the conceptually they are the same. So, I am going to start with, in order to bring parity to what we have done in our previous class while solving this problem, I am going to choose the z component of Navier Stokes equation in Cartesian coordinate system, and I will use the shear stress form of the equation, because you would remember that the governing equation that we have obtained for that case was in terms of shear stress. So, I will choose the shear stress. The same problem can be done using the velocity form of the Navier Stokes equation. There is fundamentally, conceptually no difference between the two. So, let me write this first. This is the z component of the equation, Navier Stokes equation. The first one is the temporal term or the time varying term. These are the convective part of the momentum transfer. This is the conductive or viscous transport of momentum. Let us see what these terms are once again. This is the temporal term. Any term that contains the velocity component separately, these are convective transport of momentum. So, the entire left hand side of Navier Stokes equation is the convective transport of momentum. So, convective transport of momentum and the temporal term. When you come to the right hand side, this is the surface force part, this is the shear, and this is the body force. So, let us see how can we solve this problem. What were the assumptions that we have made while solving the problem? The first was it was a steady state. The second was 1D flow, where you only have Vz which is not equal to 0, but all other components are going to be equal to 0. No pressure acting on the system, and you only have gravity, which is the component of gravity in this direction. So, the first term would obviously be 0, since the velocity in the z direction is not a function of time. So, the reason for that, I am simply writing SS or steady state. Now, if you look at the second term, the Vx, the x component of velocity, it is not there, because only Vz is non-zero in this case, but both Vx and Vy, both are equal to 0. So, this part is 0, since Vx is 0. Similarly, this is 0, since Vy is 0. However, in the fourth term, Vz is not equal to 0, but equation of continuity, since we are going to also have assumed that it is an incompressible fluid. If this is an incompressible fluid, then what we have is that Vz is a function of z, is not a function of z only. So, Vz, if you look at the figure, is a function of x. Vz is not a function of either y or z. Depending on where the film is located with respect to its distance from the solid wall, the velocity varies. So, the velocity is 0 on the solid liquid interface, that is, at this point the velocity would be 0 and the velocity would progressively rise as we move away from the solid plate. So, therefore, Vz is a function of x, but Vz is not a function of y, Vz is not a function of z, or it is a function of y. So, therefore, del Vz del z, since Vz is not a function of z, this is going to be 0 since Vz is not a function of z. So, what I have then, the entire left hand side is going to be equal to 0. Okay. And then comes this del P del Z. This is a case where no pressure is acting, no applied pressure gradient on the system. So, this would be equal to 0. Okay. So, if this is going to be equal to 0, then what you have in here is then the Z component. Now we are going to look at the shear stresses. The Z for the Z component to be transported in the y direction, there must exist a velocity gradient in the y direction. So, for Z component of momentum to get transported in the y direction, there must be a y variation of velocity, but there is no y variation of velocity. So, Vz is not a function of y, and therefore, tau yz is equal to 0. Similarly, for Z component of momentum to get transported in the z direction, Vz must be a function of z, but we know that Vz is not a function of z. So, therefore, tau zz would be equal to 0. I will repeat it once again. The tau yz represents the transport of z component of momentum in the y direction through viscous means. Now, transport of z momentum in the y direction by viscous means will only happen when there is a variation in Vz with y. So, without the velocity gradient, velocity variation, there cannot be any transport of viscous momentum. But we understand that Vz is not a function of y. So, if Vz is not a function of y, there is no gradient in the y direction, there is no gradient of Vz in the y direction. So, if there is no gradient, then tau yz must be equal to 0. Similarly, when we come about tau zz, in order for z component to have a viscous transport in the z direction, the velocity must vary. But we understand that the velocity in the z direction is not a function of z. So, therefore, tau zz is also equal to 0. Now, we come to this part. For z component of momentum to get transported by viscous means in the x direction, Vz must be a function of x. So, we need to see, is really Vz a function of x? So, if we look at the picture over here, Vz is definitely a function of x. Okay. Vz varies with x being 0 over here and maximum over here. So, there will be a transport of z momentum in the x direction since Vz is a function of x. So, what I have then is d dx of tau xz, and I have dropped the partial sign because it is only a function of x. Tau xz or any quantity is only a function of x, they are not functions of y or z. So, of the 3 terms in the viscous transport of momentum, only one will remain. The rest are 0 because of our conditions, because of our understanding. Now, now we come over here. Gz is the component of body force in the z direction, and from the figure you can clearly see that the component of gravity in the z direction is simply g cos beta. So, your this would simply be equals to g cos beta. And if you look at your previous, the one that we have done in the last week, this is exactly the same governing equation that we have obtained. So, there is no need at all to think about a shell, make balances along and across the surfaces, find out what are the pressure forces and so on. The only job that you need to do is simply choose the relevant, the right equation component for Navier Stokes equation in the appropriate coordinate system. After that, use your understanding, the description, the physics of the problem, cancel the terms which are not relevant. What you will be left with is the governing equation. So, it is a very simple way to arrive at the governing equation, and once you arrive at the governing equation, the rest will be identical. That means you are going to integrate it in the same way, you are going to use the same sort of same boundary conditions, and you will end up with the same solution, but in a much more structured and easy way. So, in the next problem what we are going to see is the same problem where we have a flow through a tube in which there is going to be a pressure gradient and there is going to be the action of gravity, which has led to the Hagen Poiseuille equation in the problem that we have dealt with before. So, our next problem is analysis of flow through a vertical tube when there is a pressure gradient active in the system. So, what we have then is a tube of, this is the radial direction, this is the z axial direction, you have some pressure P naught over here and you have some pressure P L over here, and as a result of which you are going to have flow in and flow out of the system. If you remember previously, we had to think of a shell like this, and in that shell we have found out what is the amount of liquid coming through the annular top surface, what is the shear stress that is acting inside and so on. But we need not do anything of that sort right now. Okay. What I need to do only is find out, use the right component, the right component of the equation over here. This is a cylindrical coordinate system problem, r theta z. I am going to choose the cylindrical coordinate. The principal direction of motion is in the z direction. So, I would choose the equation b dot 5 dash 6, which is nothing but the z component of equation of motion in cylindrical coordinates. So, this is the last equation I am going to choose as the starting point to derive the governing equation for this specific problem. Okay. So, I am going to write this equation in first. The equation is nothing but the z component of equation of motion, which from the text would simply tell you rho del Vz del t, the temporal term, Vr del Vz del r plus V theta by r del V theta by del theta plus Vz del Vz by del z. Since it's a cylindrical coordinate system, the terms are slightly more involved and complicated, but ultimately it wouldn't matter because we would be able to simplify it to a large extent. This is the pressure term, and then what I have over here is the viscous transport of momentum and also you have the body force term. Now I'll write this as term 1, 2, 3, 4, 5, 6, 7, 8 and 9. So what were the descriptions of the problem that we have done over here? That is, it is 1D flow. That was the same assumption that we have used. I'm just repeating the assumptions that we have made over there. Flow only in Z direction. It's incompressible flow. Vz is not equal to 0 and Vz is a function of r. Vz is not a function of theta or of z, and all the other components Vr and V theta would be equal to 0. So these were the basic assumptions that we have made in solving the previous problem. In the another one which I missed is it's a steady state condition. Okay. So we would like to see whether or not it's what happens to term 1 over here. Will it remain in the governing equation, or I can cancel it? If you look at term 1 and see steady state, so term 1 has to be equal to 0 since it's a steady state problem. What about term 2? Term 2 is this term, and if you look here, it would simply tell you that term 2 would also be equal to 0 since your Vr is equal to 0. About term 3, the same thing, term 3 would also be equal to 0. This is my term 3 since V theta is equal to 0. Term 4, Vz is not 0, but del Vz del Z is 0, because since Vz is not a function of Z. Okay. So this is 0 since Vz is not a function of Z. So the entire left hand side of the expression is 0. The temporal and the convective transport of momentum for this specific problem is going to be equal to 0. Now what about term 5? The variation of pressure with Z. I know that the pressure over here is P naught, the pressure over here is PL. So 5 is not equal to 0. There is a pressure gradient that acts on the system. Now the remaining is the Z component gets transported in r direction is the significance of tau r Z. So in order for Z component to get transported in the r direction, there must be variation in Vz with r. Do we have variation of Z in r? Let's see over here. The velocity Vz is a function of r. So obviously the velocity varies with r, and therefore tau r Z is non-zero and cannot be neglected from this equation. So this is not going to be equal to 0. But how about Z component getting transported in the theta direction? In order for that to happen, the Z velocity must change with the theta direction, which it does not, because velocity is not a function of theta. So your 7th term is equal to 0 since Vz is not a function of theta, therefore it leads to tau theta Z to be equal to 0. 8th term, tau ZZ, Z component in Z direction. For that to happen, the velocity must be a function of Z, but velocity is not a function of Z. So your term 8 is also equal to 0. And how about your term 9? Term 9 is rho g z. There is definitely a non-zero component of gravity in the z direction equal to plus g. So, this is not equal to 0. So, what I have then out of the governing equation is this would be 0, and only these three terms, term 5, term 6 and term 9 would remain in the expression. And when that happens, this equation takes the form as minus del p del z plus 1 by r, sorry, minus 1 by r del r of r tau r z plus rho g. And since you have your velocity is a function of z only, the velocity is a function of z only, essentially I can write this expression as 0 equals minus del p del z minus 1 by r d dr of r tau r z. There is no need to write a partial one now, and this governing equation, if you look at, it's identical to the one that we have derived in the previous class by writing a shell, by imagining a shell and getting all the momentum in and out terms of this. And this was solved using the condition that velocity is 0, Vz is 0 at small r equals capital R, which is the no slip condition, and your tau rz has to be finite at r equals 0. So, once you reach this point, then the rest of the solution would be identical to the one which you have done before. Now, what you then see here is you do not need to think of a shell right now. You do not need to individually evaluate and balance all the mechanism by which momentum can come into the control volume, the forces and so on. All you need is simply choose the expression, the right expression of Navier Stokes equation in the correct component form. So, the table that is provided, from that you choose the equation, and then you look at the equation and think carefully, should that term remain based on my understanding and the statement of the problem? Is there a temporal term? Is it an unsteady state process or a steady state process? Then look at the components, each components of the velocities. Are all Vx, Vy, Vz present in the system, or it's a 1D flow, therefore only Vx is present, and I can safely neglect any term containing Vy and Vz and only have the term containing Vx. In some cases it is not the velocity, but it is the velocity gradient which is important. Is it an 1D flow where you have Vx, non-zero Vx, but Vx is not a function of x, Vx is a function of some other dimension, let us say z. So, Vx may not be 0, but del Vx del x is 0. Therefore, the term which is Vx del x, that term would be equal to 0. So, what you would see in most of the cases, most of the simple problems, the entire left hand side of the Navier Stokes equation, which represents convective transport of momentum, can be set to 0. And then you come to the right hand side. The first term is the pressure gradient term. Is there any imposed pressure in the system? If not, then that term can also be dropped. The last term is the gravity term, the body force term. Is there any body force term present in the system? If so, choose the right component of gravity in order to evaluate what is the force, which is the body force which is acting on the control volume on the fluid. Once you are done, then what you have is essentially the viscous contribution of momentum transport. and there you would see that from the looking at the two subscripts, let us say tau y x, it's the x component of momentum getting transported in the y direction because of a gradient in velocity Vx that exists in y. So, x component can get transferred in y only if there is a variation in velocity in the y direction. Do we have that? So, look at the subscript and think whether or not there should be any stress in the prescribed direction due to motion due to the principal direction of motion. So, there also you would see that many of these some of these shear stress contribution to the overall momentum transfer can be neglected. Okay. And after you cancel all the terms that are not relevant to the problem at hand, what you are left with is the governing equation. That governing equation can then be used, can then be integrated. That is a differential equation. It can be integrated with relevant boundary conditions to obtain what is the velocity distribution. The functional form of velocity as a function of the x, y, z, and in some cases time as well. So, this differential approach of using Navier Stokes equation would give rise to a compact velocity expression in many of the cases, not in all, but in many of the cases. So, in subsequent lectures we would see applications of Navier Stokes equation in slightly more complicated geometries and how to solve them. In some cases we will get a nice compact analytic solution, in some cases we may not. But the concept behind the Navier Stokes equation and the ease of using Navier Stokes equation to obtain the governing equation for a given flow condition will always supersede any other method, especially the shell momentum balance. That is all I wanted to convey in this lecture. Thank you.